A very good morning to all of you. We have come to the last lecture in this topic on electromagnetism. In the last lecture, I started discussing about electromagnetic waves and how the introduction of the displacement current term in the Maxwell's equations leads to the generation or the prediction of waves called electromagnetic waves. So, today what we are going to do is I am going to show you that the electromagnetic waves which I wrote down last time are consistent with the Maxwell's equations. Now, ordinarily what we will do normally is that we will take those Maxwell's equations and derive what is called as a differential equation from those equations, and then by solving the differential equations we will get that there are waves present in the predicted by these equations, and those are called the electromagnetic waves. Now, because differential equations are beyond the scope of this course here, I will be assuming a solution of electromagnetic waves and showing that those solutions are consistent with the Maxwell's equations we have been looking at throughout this course of lectures on electromagnetism. So, let me recall, electromagnetic waves are nothing but waves of electric and magnetic fields. So, we had drawn a figure last time. For example, if I were to draw the figure, same figure again here, I will show the electric field like this, a wave like this, and these are the electric field vectors which I am drawing here. This is the z direction, this is the x direction, and this is the y direction. So, the electric field is pointing in the x direction, and the corresponding magnetic field I had drawn like this. So, the magnetic field lines are magnetic field vectors are perpendicular to the electric field vectors. So, as the figure shows, when the wave is propagating in the plus z direction, the electric field and the magnetic fields are perpendicular to the propagation direction. This is the magnetic field here. The electric field and magnetic field are perpendicular to the propagation direction of the electromagnetic wave. The electric and magnetic fields are perpendicular to each other, and both are perpendicular to the propagation direction of the electromagnetic wave, and also they are in phase. As you can see here, when the electric field is 0, magnetic field is 0. When the electric field magnitude increases, the magnetic field magnitude increases, and these are called sinusoidal waves, as I had defined last time. Sinusoidal waves. Because the space and time dependence of these waves, as I will write on an equation, are sine waves, sinusoidal waves, and so the electric and magnetic fields are in phase. And as I mentioned last time, one has to be very clear in interpreting this figure. These lines only represent the magnitude and direction of the electric field and the magnetic field at different points along the axis of the figure here. So, there is nothing, there is no movement like this, there is no displacement, it is simply the electric and magnetic fields which are varying with time at different points. So, and I must mention here now that all electromagnetic waves travel at the same speed in free space, and that value is 2.99792,458 into 10 to the power 8 meters per second. This is an exact value now. This is defined as an exact value of the velocity of speed of light in free space, and the unit of meter length unit, which is the meter, is defined through this velocity of light or the speed of light in free space. And so, all electromagnetic waves travel at the same speed given by c in free space, and in the last lecture I had shown a spectrum which shows different electromagnetic waves, radio waves, microwaves, light waves. In between you had infrared waves, ultraviolet, then you have X-rays, gamma rays. All these represent electromagnetic waves. All these are characterized by electric and magnetic fields, and they all travel in free space at the same speed, which is given by this number c, and this we normally approximate by 3 into 10 to the power 8 meters per second. So, that is an approximate value. 3 10 to the power 8 meter per second is an approximate value. the exact value as defined now is 2.99792,458 into 10 to the power 8 meter per second. So, now what I want to do is the following. I want to consider a sinusoidal electromagnetic wave, and I will show you that this solution which I am going to write is consistent with Maxwell's equations. So, sinusoidal electromagnetic wave. So, in this figure as I have shown here, the electric field is pointing along the x direction and the magnetic field is pointing along the y direction and propagation is along z. So, this kind of wave will be represented by equations of this form: E is equal to I cap E naught sin k z minus omega t. This I cap represents the fact that the electric field is pointed along the x direction. E naught is the magnitude of the electric field, the maximum value of electric field, and the sign function is actually this. And let me remind you that this is a plot of electric field and magnetic field as a function of position at a given instant of time. Please remember, this is a snapshot of the magnitudes and directions of electric and magnetic fields as a function of position at a given time t is equal to 0, arbitrary time which I call t is equal to 0. I could have, like last time, I also plotted a figure showing electric and magnetic fields as a function of time at a given position. That is another figure, and when you look at a figure, be very careful in noticing what the figure represents precisely. So, this is the electric field and the corresponding magnetic field as I have drawn here is along the y direction. So, B is equal to j cap some magnitude B naught sin k z minus omega t. So, as you can see here, I am using the same sign function as the electric field, and that is because electric and magnetic fields are in phase. Both of them are represented by the same sign function sin k z minus omega t, and their magnitudes are E naught and B naught, and the directions are I cap and j cap. I also mentioned last time that E cross B, vector E cross vector B will be along the propagation direction. So, if you look at E cross B is I cap cross j cap is equal to k cap, which means propagation along z direction. So, this is what this figure represents. E cross B cap, E cross B must be along the propagation direction. So, this is a wave propagating along the z direction, having magnitude E 0 of electric field, a magnitude B 0 of magnetic field, both of them are in phase. Now, what I am going to do is the following. I am going to show you that these two equations are consistent with Maxwell's equations, and for this I am going to look at free space. So, I am looking at propagation of electromagnetic wave in free space. That means there is no medium and there is no charge, no charges, no currents. So, the electric and magnetic fields satisfy the following equations: E dot d A is equal to 0, integral B dot d A is equal to 0, integral E dot d L is equal to minus d by dt of integral B dot d A, and integral B dot d L is equal to mu 0 epsilon 0 d by dt of integral E dot d A. That is the Gauss's law for electric fields, the Gauss's law for magnetic fields, Faraday's law of induction, and the generalized Ampere's law. And in all this I have removed the charge from here on the right hand side. So, there is 0 here, there is no current on the right hand side. So, there is no current. So, there is no term corresponding to current here, and these equations contain only electric and magnetic fields. And what I am going to show is that the solutions which I have written, namely these two solutions, are consistent with the Maxwell's equations. Now, let me recall again that these two equations tell me that a changing magnetic field will generate an electric field, and a changing electric field will give me a magnetic field. A time varying magnetic field will lead to an electric field, and a time varying electric field will lead to a magnetic field. This is the way the electric and magnetic fields couple to each other, and this is the way the electromagnetic fields are propagating and generated through the space, and these waves do not require any medium to propagate. Unlike other waves like sound waves or water waves or waves on a string, in which there is a medium required, these waves do not require any medium to propagate, and so these waves can propagate through free space right from stars which are light years away. The light coming from there is essentially electromagnetic character. Now, what I am going to show you is the solutions which I have written, namely these two solutions are consistent with these two equations. That means that the magnetic field as given by this equation and the electric field given by these equations and the corresponding these two solutions, these two equations, this equation here, the solutions are consistent with this. So, let us start from Faraday's law first. So, I want to show that the solution which I am writing, I want to find out under what condition the solution which I am writing is consistent with this equation minus d by dt of integral b dot dA. Now, for this let me again draw a figure. X, Y, Z. So, I draw the electric field variation like this and the magnetic field variation is like this. I am just looking at a part of the wave, and let me draw again here. The magnetic field lines are pointing like this at this instant of time, and the electric field lines are pointing upwards at this instant of time. Okay. Now, what I want to do is the following. I want to consider a loop here, which I call P, Q, R, S, and I want to do an integration in this direction. Look here, the left hand side has a integral over a closed path and the right hand side has the magnetic flux. So, I take a loop P, Q, R, S in the xz plane, and I want to find out that under what conditions am I satisfying this equation. So, there is an electric field here and there is a magnetic flux passing through this. So, the area which I am looking essentially is this area. So, I have magnetic field lines crossing this area which is in the y direction, and there is an electric field which is present in the space here. So, let me write down. So, I want to calculate the left hand side for this path and the right hand side for this path and equate them and get an equation. Now, let me assume that the height of this loop is h, and this is the plane z is a z, and this is a plane I call it z plus delta z, and delta z is infinitesimal. Very small value of delta z. So, it is a very small number, and I want to calculate the left hand side and right hand side. So, first let me start with the left hand side. So, I want to calculate integral E dot dl. So, look at the path here, the path I am taking is P Q R S. So, this will be equal to integral P to Q E dot dl plus integral Q to R E dot dl plus integral R to S E dot dl plus integral S to P E dot dl. And I know the electric field was given by I cap E naught sin k z minus omega t. Now, so the electric field is along x axis. So, if you see already here along the path q r, electric field is perpendicular to the dl, dl vector is along q r, electric field is perpendicular. So, E dot dl in this path will be 0. Similarly, for the path SP, E is perpendicular to this line, and so E dot dl is 0. So, the integrals from this integral q to r and s to p are 0. The remaining two integrals E is the same for all values of x, because E depends only on z, and the value of electric field at z and z plus delta z will be different, because as you can see here the electric field is changing with z. So, I will get this is equal. So, integral E dot dl will be equal to, essentially you will have two components, p to q E dot dl plus r to s E dot dl. The remaining two integrals have become 0, and so p to q E dot dl. So, this is nothing but electric field at z plus delta z into the total length, because electric field is constant along this length and dl is parallel to electric field. So, E dot dl is E dl and E is constant along this path. So, this will into this length h is this length of integration. And then, so in the second part r to s, you see here electric field is pointing upwards, the path of integration is from r to s. So, I will get a negative sign, E dot dl will be negative and I will get minus E of z into h. So, this is nothing but E of z plus delta z minus E of z into h, and delta z is a infinitesimal quantity. Now, let me recall to you, you have defined the differential of a function d. So, let me take a function df by dx is equal to limit delta x tending to 0 f of x plus delta x minus f of x by delta x. There is a definition of a differential of a function, limit delta x going to 0 f of x plus delta x minus f of x by delta x. So, if delta x is very small, extremely small, then I can write this as df by dx. If I choose a very small value of delta x, this is approximately equal to f of x plus delta x minus f of x by delta x. So, this I can write as f of x plus delta x is equal to, if I simplify this, I will get f of x plus delta x times df by dx. So, the value of a function at x plus delta x is equal to value of the function at x plus delta x into the derivative of the function with respect to x at this point. So, this is a nice expression. In the limit of delta x becoming very small, I can use this kind of an expansion of f of x plus delta x is equal to f of x plus delta x into df by dx. Now, if you look at this equation and this term here, it is E of z plus delta z minus E of z. This is f of x plus delta x minus f of x. So, I can write immediately E of z plus delta z minus E of z by delta z is equal to dE by dz, which means that E of z plus delta z minus E of z is nothing but delta z times dE by dz. So, E of z plus delta z minus E of z is nothing but dE by dz into delta z. So, I get the following equation, integral E dot dl is equal to so dE by dz into h delta z. Now, I must mention something here, that remember this function, this electric field E is a function of both position z and time, and because my derivative is with respect to one of the variables position, this is usually written as a partial derivative. So, this is in mathematics, this is written as del E by del z into h delta z. This only means that I am taking a derivative of the electric field as a function of z, keeping time constant. The electric field is a variable which depends on position z and time t, and here in this derivative all I am saying is I am taking a derivative of the function with respect to z, keeping time constant. So, I am writing this as del E by del z. It implies it is called a partial derivative. It is a derivative of the function with respect to one coordinate, keeping the other coordinate constant. So, what I have got is integral E dot dl is del E by del z into h delta z. Now, let me look at the right hand side. There is a right hand side of this integral here of this equation, which is integral B dot dA. Now, I must calculate the flux through this area. The first thing you notice is because the integration is in this direction, the area vector is along this direction. Because the loop integration which I have done is anti-clockwise, area vector is in this direction, which is nothing but y cap j cap. So, area vector for this loop of integration is along the direction y, which is also the direction of the magnetic field. So, I can immediately calculate integral B dot dA is equal to, now remember delta z is a very small quantity, and so I can assume that the magnetic field is almost constant between z and z plus z delta z. In this area, magnetic field is almost constant. So, this is approximately equal to magnetic field at z into area of this entire loop is h times delta z into h delta z. So, Faraday's law, for Faraday's laws I must calculate d by dt of integral B dot dA, which is nothing but, I will again write as before, del B by del T into h dz. Because magnetic field depends on position and time, I am differentiating with respect to time, and so I write as a partial derivative of B with respect to time into h delta z. So, that I have got, and I have got the left hand side of the Faraday's law. So, left hand side is so much. So, I just substitute into this equation. So, I substitute both of these into the following equation, E dot dl is equal to minus d by dt of integral V dot dA. So, integral E dot dl I have calculated as del E by del z h delta z, and this is minus del B by del T h delta z. This implies del E by del z is equal to minus del B by del T. So, Faraday's law implies del E by del z, rate of change of E with z, is equal to minus of del B by del T. Now, if I substitute the solutions which I have written before for electric and magnetic fields. So, let me write the equation again here. So, I have shown that del E by del z is equal to minus del B by del T. Now, E was equal to the scalar form, if E was equal to E naught sin k z minus omega t. So, del E by del z is equal to k times E naught cos k z minus omega t. B was equal to B naught sin k z minus omega t. So, del B by del t will be equal to, now there is a minus sign here. So, I will get minus omega B naught cos k z minus omega t. So, this is del E by del z, this is del B by del t. So, I substitute here and I get this cosine function cancels off and I get k times E naught is equal to omega times B naught. So, I have got an equation, that means if the electric and magnetic fields were given by those equations, the solutions, then I find that for those solutions to satisfy Faraday's law of induction, the magnitudes of the electric and magnetic fields must be related to this equation, k E naught must be equal to omega B naught. That is first equation which I have got. Now, I want to apply the same solutions in Ampere's generalized Ampere's law. So, now let me look at Ampere's law was integral B dot dl is equal to mu 0 epsilon 0 d by dt of E dot dA. So, I need to calculate both the left hand side and the right hand side. So, let me draw the figure again here. So, I again have the electric field going like this, and I have the magnetic field like this. Now, I take a loop in the other plane. So, I take a loop like this. So, this is again this is point z, this is point z plus delta z. So, I take P Q R S. Now, I take a loop in the yz plane. So, this is z, this is x, this is y. This loop now happens to be in the yz plane, and so we have electric flux crossing this plane and there is a magnetic field. So, I want to calculate integral B dot dl in this loop and the right hand side for this area which is enclosed by this loop, and substitute into this equation and find out again a relationship between the electric field E naught and the magnetic field B naught. So, let me start calculating integral B dot dl. Integral B dot dl, again P to Q B dot dl plus Q to R B dot dl plus R to S B dot dl plus S to P B dot dl. So, look here, it contains P to Q B dot dl plus Q to R B dot dl plus R to S B dot dl plus S to P B dot dl. That is a complete loop. Now, just like before, look here, the magnetic field is along the y direction and this line is along the z direction, and similarly this line. So, the integral B dot dl from Q to R and S to P are 0. So, I will simply get integral P to Q B dot dl plus integral R to S B dot dl. The remaining two integrals are 0. Now, at this plane in this line, the magnetic field is calculated at z plus delta z. Here the magnetic field is at z. The direction of magnetic field is along the path of integration. So, B dot dl is B dl. Similarly, here B dot dl I can calculate. So, I will get this is equal to nothing but B at z plus delta z into, again I will assume that this distance is h as before. So, B at z plus delta z into h. Now, look here, in the R to S integral, magnetic field is pointing along y direction and my integration is along the minus y direction. So, I will get a minus sign. So, I will get minus B of z into h, which is nothing but B of z plus delta z minus B of z into h. Now, as before, B of z plus delta z minus B of z is approximately equal to delta z into del B by del z. Using again the same argument as I had given for calculating del E by del z, I can write immediately that, like here, remember I had written here E of z plus delta z minus E of z was delta z dE by dz, B of z plus delta z minus B of z is approximately delta z del B by del z. So, integral B dot dl will be equal to del B by del z into h delta z. Again I am writing partial derivative because the magnetic field depends on position and time, and so this is a derivative with respect to z keeping time constant. Now, I must calculate the right hand side, which is depends on the electric flux E dot dA. So, here this is the area enclosed by the loop, and remember now the integration is in this direction P Q R S. So, the area must be pointing down. This, using right handed rule, this is the path of integration is in this direction, and because of right hand rule area is pointing downward, electric field is pointing upward, and so the electric flux is negative. Please remember in this equation electric field is pointing upward area is pointing downward, and so E dot dA will have a negative sign. Now, again as before, I am going to assume that the electric field is almost constant within the area of this loop. So, this integral will simply be electric field at this point multiplied by the area of the loop. So, this is equal to minus of E of z into area of the loop, which is h delta z. I am assuming that the electric field is almost constant within the area of the loop. So, E dot dA is minus E dA, because area is pointing downward, electric field is pointing upward, and electric field at this point is approximately E of z and multiplied by area, which is h times delta z. So, mu naught epsilon naught d by dt of integral E dot dA will be equal to minus mu naught epsilon naught del E by del t into h delta z. Again I am writing a partial derivative, because electric field is a function of both position z and time, and this derivative is only with respect to time. So, I substitute both of them into this integral of Ampere's law. B dot dl is equal to mu naught epsilon naught d by dt of integral E dot dA. So, I just calculated B dot dl integral. So, B dot dl integral is del B by del z h delta z is equal to minus mu naught epsilon naught del E by del t h delta z, which implies del B by del z is equal to minus mu naught epsilon naught del E by del t. So, just like I had an equation relating del E by del z and del B by del t, I have another relationship between del B by del z and del E by del t. So, if the solutions which I have written have to satisfy Ampere's generalized Ampere's law, then the electric and magnetic fields must satisfy this equation. Del B by del z is minus mu 0 epsilon 0 del E by del t. So, let me substitute the solution. So, let me rewrite this again. So, del B by del z is equal to minus mu naught epsilon naught del E by del t. Now, B was equal to B naught sin k z minus omega t. So, del B by del z is equal to k B naught cos k z minus omega t. E was given by E naught sin k z minus omega t. So, del E by del t is equal to minus omega E naught cos k z minus omega t. Differential of sine is cosine, and because there is a minus sign here, I get a minus here and omega. So, if I substitute this into this equation, I get k times B naught is equal to mu 0 epsilon 0 into omega E naught. So, that is another equation. If the solutions which I have written must satisfy the generalized Ampere's law, then E naught and B naught must satisfy this equation. So, now let me recall the other equation which I got, which is the condition to satisfy Faraday's law. So, I got two equations. If the solutions which I have written must satisfy Faraday's law of induction, E naught and B naught are related by this. If the solutions must satisfy generalized Ampere's law, E naught and B naught are related by this. So, let me rewrite these equations and simplify. So, I have two equations now. So, k times E naught is equal to omega times B naught, and k times B naught is equal to mu naught epsilon naught omega E naught. So, let me multiply both these equations. I get k square E naught B naught is equal to mu naught epsilon naught omega square E naught B naught. So, if I cancel up E naught B naught, I get k square is equal to mu naught epsilon naught omega square. So, now I got a relationship between omega and k which appear in the solutions. In the solutions there is k and omega, and remember when I was discussing waves on a string, I had defined the speed of wave as omega by k. So, omega and k are related by this. So, speed of the wave is equal to omega by k, which is equal to 1 by square root of epsilon 0 mu 0. So, this is the speed of the electromagnetic wave. What I have shown you is that I started with solutions of electric and magnetic fields in the form of a wave. Let me show you the slide again here. The electric and magnetic fields we had written in the form of a wave. Here, electric field written as sine kz minus omega t, which is a wave propagating along the z direction. Magnetic field j b naught sine kz minus omega t, a magnetic field propagating as a wave in the z direction. These two are the electric and magnetic fields associated with the electromagnetic field, and if these two have to be solutions, have to satisfy the Maxwell's equations, we find that these are waves. These are, because I have written solutions like this, these are waves and these are the electromagnetic waves, and the speed of the electromagnetic wave in free space is given by 1 by epsilon naught mu naught, which is actually called c, the speed of light in free space, and this is the speed which I wrote earlier. So, you see here that in free space, independent of the frequency of the electromagnetic wave, all electromagnetic waves, no matter what frequency you take, whether you take radio waves at megahertz frequencies or microwaves at gigahertz frequencies or light waves or X-rays or gamma rays, all these waves which consist of electric and magnetic fields propagate at the same speed c, which is 1 by epsilon 0 mu 0 square root. So, this is a very important relationship that we have got. What I have shown you today is that electric and magnetic field can propagate as waves in free space, and the speed of these waves is nothing but given by 1 by square root of epsilon 0 mu 0 in free space. So, essentially what I have not actually solved the Maxwell's equations and got solutions, but what I have essentially shown you is that if I write a wave solution of electric and magnetic fields, then I can satisfy Maxwell's equations. These solutions satisfy Maxwell's equations provided these waves travel at the speed which is given by 1 by epsilon 0 mu 0 square root, and this was the prediction of James Clerk Maxwell. And when he found that the speed of light is the speed of the electromagnetic wave is related to the epsilon 0 constant and mu 0 constant, and the value of c which he obtained from this equation was so close to the velocity of light in free space, the measured speed of light in free space, that he predicted that light must be electromagnetic. And as I mentioned before, it was Hertz in 1888 who conducted experiments and showed the generation and detection of these electromagnetic waves, and then we know that electromagnetic waves exist at all kinds of frequencies, and we have given them different names for different frequencies. And just like before, the speed of electromagnetic waves in free space is c, which is approximately 3 × 10⁸ meter per second. And remember, the wavelength of the electromagnetic waves is equal to lambda, which is c by nu. So, different frequencies are characterized by different wavelengths. These are all wavelengths in free space. So, I will urge you to substitute the values of frequencies for radio waves, microwaves, light waves, X-rays and gamma rays, and calculate the wavelengths, and you will see typically radio waves are in the range of a few hundred meters of wavelength, microwaves are in centimeters, light waves are in nanometers, X-rays are even much smaller than that, fraction of a nanometer, and then you have gamma rays in the range of picometers. So, the wavelengths range over an entire range of wavelengths and similarly frequencies. So, these are all electromagnetic waves. Now, once I have got these electromagnetic waves, remember I have shown you long time back to when we were discussing electrostatics and magnetostatics, that electric and magnetic fields have energy stored in them, and the energy stored is given by, so energy stored, energy in electromagnetic waves. So, I had shown before that the electrostatic energy density is half epsilon 0 E square, that is electric energy density, energy per unit volume. Similarly, the magnetic energy density is 1 by 2 mu 0 B square. Now, we have got these two solutions here, and I have shown you the speed as 1 by epsilon 0 mu 0 square root. So, also note this equation, let me see what that implies, k E naught, let me rewrite that equation. So, k times E naught is equal to omega times B naught. This implies B naught is equal to k by omega into E naught, and k by omega is 1 by c. So, this is equal to E naught by c. So, if E 0 represents the maximum value of electric field in the electromagnetic wave, the maximum value of magnetic field in the electromagnetic wave is E naught by c, where c is the speed of light in free space. So, this is a very important relationship. Again, I must remember that in free space the electric and magnetic fields of the electromagnetic wave are related through B naught is equal to E naught by c. So, let me substitute this here for example, and what I get is u b becomes equal to, u b was 1 by 2 mu 0 b square, which is equal to 1 by 2 mu 0 b naught square sin square k z minus omega t, which is equal to 1 by 2 mu 0. Now, B naught was E naught by c. So, E naught square by c square sin square k z minus omega t, and this is 1 by 2 mu naught. Now, 1 by c square is epsilon 0 mu 0 E naught square sin square k z minus omega t, which is nothing but 1 by 2 epsilon 0 E naught square sin square k z minus omega t. That is the magnetic energy density. The electric energy density is 1 by 2 epsilon 0 E square, which is nothing but 1 by 2 epsilon 0 E naught square sin square k z minus omega t. So, you see that because of this relationship B naught is equal to E naught by c, what you find is the energy density of the electric field in the electromagnetic wave and the energy density of the magnetic field in the electromagnetic wave are exactly equal. Both are equal to half epsilon 0 E naught square sin square k z minus omega t. So, the electromagnetic wave as it propagates is carrying this energy as it propagates. So, I can write the total energy density u is equal to u e plus u b, which becomes equal to epsilon 0 E naught square sin square k z minus omega t. I have added these two. This is the electric field energy density, magnetic field energy density, they are equal, and so I get epsilon 0 E naught square sin square k z minus omega t. Now, this is a time varying and a position varying function. As you can see, it varies as sin square k z minus omega t. Now, at optical frequencies, the frequency is very large. So, it is very difficult to follow this. So, what we normally do is to calculate a time average. time average of this energy density, and I can calculate the time average as 1 by. So, let me call this u dash 1 by t integral 0 to t u dt. I integrate over one period of the wave, where so t is equal to 2 pi by omega. So, I integrate over one period of the wave, divide by the time of integration, and I get an average value. So, to calculate an average, I integrate over a certain region and divide by that width of that region, and I get an average. So, this is equal to epsilon 0 E naught square by t 0 to t of sine square k z minus omega t dt, with t given by 2 pi by omega, and I believe it is a problem to you to show that this is equal to half of epsilon 0 E naught square. So, you show that 1 by t integral 0 to t sine square k z minus omega t dt is actually half. You must know that the average of a sine square function is half, the average of a cosine square function is half. So, that average is half, and that is the time average total energy density associated with the electromagnetic wave, and this energy is actually propagating like here. So, I can actually look at the following situation. So, I have, let me take a unit area. So, this is a unit area and length c. I take a cube with length a cuboid with length c and a unit area. So, as you can see here, the waves are propagating in this direction, this is the direction. So, in a unit time, all the energy contained within this volume will cross this area. All the energy that is contained within this volume will cross this area. So, I can calculate average energy crossing unit area per unit time as equal to energy density into the volume, which is C into 1, which is equal to 1 by 2 C epsilon 0 E naught square. So, this energy which is contained in the electromagnetic waves is propagating, and in a unit time the energy contained in this volume of length c and unit area will cross this surface, and that energy happens to be this, and this is also called as intensity. And usually referred to as I. So, intensity of the electromagnetic wave is given by half f c epsilon 0 E naught square. So, intensity and the electric field are related through this relationship, very important relationship. If you know the intensity, if you know the power crossing per unit area per unit time, then you can calculate the corresponding electric field here. And so, let me write this equation again here. So, I is equal to 1 by 2 C epsilon 0 E naught square, and E naught is also equal to square root of 2 I by C epsilon 0. So, if you know the intensity, you can calculate the electric field. If you know the electric field, you can calculate the intensity of those waves. Now, so what we have done now is we have actually written down electric and magnetic fields as waves, and I have shown you that the solution which I wrote down is consistent with Maxwell's equations, satisfy Maxwell's equations, provided I take the speed as c and I get a relationship between the magnitude of electric and magnetic fields, and this is what the prediction was. Now, I want to take a few examples and calculate what kind of electric fields are generated in typical situations. So, first example which I want to look at is sunlight, light from sun. Light is an electromagnetic wave. The sunlight is falling on the earth. As it comes outside the earth, it is much higher, but as it propagates through the earth atmosphere, it gets scattered. So, finally, the average intensity on the earth as it falls on the ground is approximately 1000 watts per square meter. That is unit of intensity, so much power per unit area, that is intensity, which is watts per square meter. So, I can use this. I am assuming that it is a single frequency wave and it is just on an average. I can use this equation to calculate the electric field. So, E naught, the electric field of the sunlight, is equal to 2 I by C epsilon 0, which is equal to right per half, which is equal to 2 into 10 to the power 3 by velocity of light in free space 3 10 to the power 8 into epsilon 0, which is 8.85 10 to the minus 12 raised to the half, and this comes out to be approximately 870 volts per meter. So, the sunlight is producing a voltage electric field of about 870 volts per meter, and I can also calculate the corresponding magnetic field. B naught is equal to E naught by C, which is equal to 870 divided by 3 10 to the power 8, which is approximately 3 into 10 to the minus 6 Tesla. An electric field of the order of 870 volts per meter and a magnetic field of the order of 3 micro Tesla. So, the electromagnetic waves from sun is creating these kinds of electric and magnetic fields. Let me take another example. There was a satellite launched in 1977, which is called Voyager 1 in September 1977. It has traveled over all the last 30 years or so, and it has left the solar system and it is out into the space, and so the current distance is about 2 into 10 to the power 13 meters, and the transmitter power is about 20 watts. Now, this transmitter is not transmitting in all directions, but it is a form of an antenna. You must have seen the antenna that you are using for cable television antennas. So, there is an antenna which actually directs the waves into a particular direction, and so instead of the electromagnetic waves going in all directions, you can actually reduce the spread of these electromagnetic waves and increase the intensity of the electromagnetic wave in the direction that you want, and so we define what is called as the antenna gain, which is approximately 6.5 into 10 to the power 4, which is essentially it gives me how much increased intensity that I get, because I am now directing the electromagnetic waves in one particular direction and not radiating in all directions, and I can then calculate the received intensity, which is equal to 20 watts is the power emitted. There is a gain of 6.5 10 to the power 4 divided by 4 pi into distance square, which is 2 into 10 to the power 13 square. And if you calculate this, it comes out to be about 2.6 10 to the minus 22 watts per square meter, an extremely small value of intensity that is coming here from that Voyager spacecraft, and we can actually calculate immediately the corresponding electric field. Electric field is 2 I by C epsilon 0 raised per half, and that comes out to be 4.4 10 to the minus 10 volts per meter, and the magnetic field is equal to E naught by C, which is approximately 1.5 into 10 to the minus 18 Tesla. It is a very small electric and magnetic field that is coming from the spacecraft, and our detectors here are able to detect these signals. And one final example which I want to give you is a laser. Suppose I take a laser. All of you must have seen laser pointers. So, they have typically, if I take a laser power of 10 milliwatts, which is equal to 10 to the minus 2 watts, and if I assume the radius of the laser beam is about 1 millimeter, then the intensity is equal to power by area, which is equal to 10 to the minus 2 by pi into r square, which is 10 to the minus 6 meter square. So, that is equal to 10 to the power 4 by pi watts per square meter, and I can immediately calculate E naught, which is 2 I by C epsilon 0 raised per half. That comes out to be 1.5 kilovolts per meter, and the corresponding magnetic field is E naught by C, that comes out to be 5 10 to the minus 6 Tesla. So, you can see that the power levels are quite strong here, that is about 1000 watts per 3000 watts per square meter, and the corresponding electric field is the magnetic fields. So, these were 2 or 3 examples which I thought may be of interest to you, that you can actually calculate from the intensity of these electromagnetic waves, you can actually calculate the corresponding electric and magnetic fields. And so, what we have done, so we have now come to the end of this course on electromagnetism. So, let us recall, we have through the lectures, the past lectures, we have obtained laws which describe electric and magnetic fields. We try to understand what are these electric fields and what are the magnetic fields. We wrote down equations, and finally, we combined all the equations into a set of equations called Maxwell's equations. Maxwell added a very, very important contribution to Ampere's law in that equations, and which we called as displacement current, and we got 4 very, very important equations which describe all of electromagnetism. So, those equations along with Lorentz force law, which we have already used, give us complete electromagnetic behavior of all systems that you can imagine, and so these equations form a very, very important part of physics engineering. We are using electromagnetic waves in so many applications. Our communications today, our mobile communications depends on radio waves or microwaves. We have light waves which are being used for various applications. We have communication satellites transmitting radio waves from far off distances. We are using electromagnetic waves over all possible applications, and these form a very, very important component of our society. And I think we have been able to use this, using these equations, try to understand some of the physics, very interesting physics behind electric and magnetic fields, and how we can generate and propagate electromagnetic waves in free space. It is a very, very important aspect that these waves do not require any medium to propagate. So, you have electromagnetic waves propagating in free space, and this velocity, the speed of light c, which is here, forms also the basis for the special relativity which Einstein had postulated. And so, I hope I have been able to convey you some of the excitement and interest and wonderful physics behind the Maxwell's equations and the kind of predictions that they give. There is a lot more to understand for all of you. We have not discussed electromagnetism in materials, electromagnetic waves in materials. So, we can actually further understand many of these, and as I mentioned in the first lecture, very interesting concept of metamaterials and negative refractive index and so on. So, all these come under purview of electromagnetism. We can actually form structures, we can design structures in which we can get very interesting properties of electric permittivity epsilon and magnetic permeability mu. And so, these are a form of a very, very important aspect of physics today, and I hope you have enjoyed the course of lectures on electromagnetism and wish you all the best. Thank you.